Hello viewers, how are you? Welcome to my channel Physics with Friends. So today we are going to discuss about heat transfer in the case of conductors. So before going to start this topic, those who are new to my channel, please subscribe my channel so that you can receive notifications regarding my channel, as well as you can clear your concepts and you can solve as many numericals as you can. So before going to start this topic, as I said previously in my videos, once again I am realizing that understanding physics is very easy. So by analyzing, you can understand the physics in an easy manner. So let's enter into the topic. Heat transfer. Commonly, the heat transfer takes place in three processes. One is conduction, and the second one is convention, and the third one is radiation. So as you observe that conduction process takes place when two bodies are in contact. Means if I consider a hot body as well as a cold body. When these two bodies are being connected by using a rod. If we connect these two bodies, without the transfer of matter, heat is being transferred from higher temperature body to lower temperature body. Here the condition is that T1 is greater than T2. This process is known as conduction. In the case of convention, matter transfer takes place and heat is being transferred from one place to another place. Let us consider water in a beaker. So when we consider water in a beaker, and if we heat the beaker, here the heat is being absorbed by this water. As it absorbs the heat is being transferred from bottom to up due to the transfer of matter. Means water is being shifted. Why? Because as the water absorbs the heat, density of the water decreases. So cold water will have more density. Due to this reason, the cold water moves down, whereas hot water moves up. In this way, heat is being transferred from one place to another place. This process is known as convection. In the case of radiation, heat is being transferred from one place to another place without the movement of matter as well as without the joining of two bodies. So in this process is a natural process and we can observe it in real life, light transfer. After that, as the light is being transferred from sun to earth, along with light, heat radiation is being transferred. So this process is known as a radiation. So now we are going to discuss about conduction. In the case of conduction, observe that we have considered two bodies. One is a heat body and one is cold. So heat transfer takes place from one body to another body, from hot end to cold end, when there is a temperature difference. So this process is known as a conduction. As you observe that here we consider two conditions. So one is a variable and the second one is a constant. Variable heat as well as constant heat. In the case of a variable heat transfer, heat at every unit part will be different due to the difference in the heat from one part to another part. Heat is being transferred from higher temperature to lower temperature. Whereas the second one is constant heat throughout the body. If the heat is constant throughout the body, here we can represent that there is no temperature difference. When there is no temperature difference, heat cannot be transferred from one end to another end. Why? Because it's the same, it's constant. So as it is constant, heat cannot be transferred. Okay? Take a screenshot, we'll continue. Now we are going to discuss about the heat transfer in the case of conduction. For this, we consider a rectangular conductor of length L and area A. So, as you observe that area of this conductor is A and length of this conductor is L. Now, when we maintain different temperatures at both ends of this conductor, heat is being transferred from hot end to cold end. Means we represent that here at this end temperature is higher as compared to temperature at this end. Means we are representing that T1 is greater than T2. So it's hot end and this one is the cold end. So when we maintain the temperature difference across the ends of a rectangular slab, so heat is being transferred from hot end to cold end through the slab. Now based on that, as the heat is being transferred from this end to this end, the flow of heat through the slab is directly proportional to area of the slab. Whereas heat flow through the slab is directly proportional to temperature gradient, where temperature gradient is represented as delta T by delta X, where delta T is the change in temperature, where delta X is the change in distance. So with respect to distance, the change in the temperature is represented as a temperature gradient. And next, as you observe that as the heat is flowing through the body, it is directly proportional to change in the time. Change in the time. So now instead of representing all these equations, we combine this equation and we represent it as delta Q is directly proportional to A into delta T by delta X into delta T. So this represents the equation in the case of heat is transferred from one end of the rod to another end, nothing but conduction. So here when we remove this proportionality, we will add a constant, where this constant is represented as K, where K into A into delta T by delta X into delta T. This represents the expression for thermal conductivity. Why? Because heat is being transferred through a body in the form of conduction. That's why we represent it as a thermal conductivity. Where K is a coefficient of thermal conductivity. So now, as you answer that, if we consider this delta T, this delta T can be represented as a T1 minus T2, change in the temperature across the ends of the rod, where delta X is nothing but change in the length. So as you consider that the total length of this rod is L, so instead of representing delta X, we consider it as a L. And here, as you observe that delta into small t represents a change in the time in the case of flow of heat from one end of the rod to another end. So we represent it as a delta T equals to T. So now the common equation can be represented as a delta Q, or the flow of heat is represented as Q, where Q is equals to K into A into T1 minus T2 by L into T. This represents the expression in terms of a change in the temperature with respect to time. So now, as you answer that here, when we bring this T towards this side, then expression can be represented as Q by T. Q by T is equal to Ka into T1 minus T2 by L, where Q by T represents rate of flow of heat through a slab. It might be any shape, either it might be rectangular, square or anything. So when heat is being transferred with respect to time, then rate of flow of heat can be given as Q by D equals Ka into T1 minus T2 by L. Whereas this Q by T can be represented as X suffix C, heat transfer through a body in the case of conduction, where X suffix C equals to Ka into T1 minus T2 by L. So as after this, here we had represented a rate of flow of heat through the slab in the case of conduction. So now take a screenshot, we will continue. Okay, now as after that we had represented Q is equals to Ka into T1 minus T2 by L into T is the equation represented by us when heat is being transferred from one end of the rod to another end, or in the case of the slab. So now as you consider this equation here, after that we can consider current flow through a conductor, and it is represented as V equals to IR. Then after that I is equals to V by R. I equals to V by R. In the same way, when we consider this equation also, that Q by T is equals to Ka into T1 minus T2 by L. So when we bring this K in a denominator, that equation can be represented as T1 minus T2 by L by Ka. L by K, where L by Ka represents the resistance to the flow of heat through the body. So after that we can represent R equals to L by Ka, just like a resistance in the case of a current carrying conductor. So here we can compare this. So in the case of heat transfer, resistance is represented as R equals to L by K. Whereas when we consider series combination of conductors, then the equivalent resistance is given as R equals to R1 plus R2. Whereas the parallel combination of resistors is represented as 1 by R equals to 1 by R1 plus 1 by R2. From this, the equivalent resistance can be represented as R equals to R1 R2 by R1 plus R2. So in this way we can represent the equivalent resistance when two conductors are connected in series as well as in parallel. Whereas remember one thing, based on this equation we can represent the conductivity of different materials. Of all the materials, silver is having high thermal conductivity. Later on, gold, copper, like that we can represent the different types of materials. So by using this equation itself we can represent the thermal conductivity of different materials. Take a screenshot, we will continue. Now we are going to discuss about the conductivity, equivalent conductivity in the case of series combination, parallel combination. So when we consider these two conductors are in series, whereas conductivity of the first conductor is K1 and conductivity of the second conductor is K2. And here we know that in the case of series, the equivalent resistance is represented as R equals to R1 plus R2. And here we know that R equals to L by Ka. L by Ka, where length of this conductor is L1 and length of this conductor is L2. After that we had connected these two conductors in series. Based on that, here we can represent that area of this conductor as well as area of this conductor is same. So now when we substitute the value of R in this equation, observe that L by nothing but sum of these two lengths, L by K into A is equals to R1 is L1 by K1 into A plus L2 by K2 into A. Observe that in the case of denominator we can take A as comma and A gets cancelled on both sides. So here we have L by K is equals to L1 by K1 plus L2 by K2. L2 by K2. So here L is equals to L1 plus L2. So when we substitute this, observe that L1 plus L2 by K equals to L1 by K1 plus L2 by K2. Then K equals to, here as you can see that K equals to, let's cross multiply this equation. K1 K2 into L1 plus L2 by K1 into L2 plus K2 into L1 is the final equivalent thermal conductivities of these two conductors when they are connected in series combination. If we consider both the lengths of these two rods are same, means if we consider L1 is equals to L2, then observe that K is equals to L plus L. Let us consider as L. So L plus L is 2L into K1 K2 by here L into K1 plus L into K2. Also that here we can take L as common. So K is equals to 2L into K1 K2 by L into K1 plus K2. Here L gets cancelled. So we get a K is equals to 2K1 K2 by K1 plus K2. The equivalent thermal conductivity when two equal lengthed rods are connected in series, then we represent it as 2K1 K2 by K1 plus K2. Suppose if the length of these two rods are different, then equivalent thermal conductivities of these two thermal conductors in series is K equals to K1 K2 into L1 plus L2 by K1 L2 plus K2 L1. Now let us observe the parallel combination. As you observe the parallel combination, in parallel combination the length of these two conductors is the same as area in the case of a series combination is same, length is same, whereas area of the first conductor is represented as A1 and area of the second conductor is represented as A2. Now here we know that 1 by R equals to 1 by R1 plus 1 by R2, and we know that R equals to L by K. So as you substitute that, observe that K into A is nothing but sum of the two areas A1 plus A2. So here Ka by L is equals to K1 into area of this conductor is A1 by L plus K2 into A2. K2 into A2 by L. Observe that we can cancel L on both sides. Then here Ka is equals to K1 A1 plus K2 A2. So from this equivalent thermal conductivity, K equals to K1 A1 plus K2 A2 by A, where A is nothing but sum of the two areas, nothing but A1 plus A2. This is the equation given for these two conductors when they have different areas. Suppose if we consider both the conductors are having equal areas and they are connected in a parallel combination. So we can substitute A1 equals to A2 equals to A. Also that here as we substitute A1 equals to A and A2 equals to A. Here we can take A as common. Then K is equals to, then K equals to A into K1 plus K2 by sum of the two areas. A plus A is 2A. So here observe that A gets cancelled. So here we get K equals to K1 plus K2 by 2 is the resultant equivalent thermal conductivity when two thermal conductors which are of equal length and equal area are connected in a parallel. Take a screenshot, we will continue. So now let's observe this problem. Here observe that at this point temperature is 5 degrees Celsius. So now this rod has been connected to with the two different rods, whereas the temperature at this end is 3 degrees Celsius and the temperature at this end is 2 degrees Celsius. Whereas the thermal conductivity of the rod is K and thermal conductivity of the rod is 2K and thermal conductivity of this rod is 3K. Now we are going to represent the temperature at the junction. Let us consider it as a T based on the rate of flow of heat. So we know that Q by T is equals to Ka into T1 minus T2 by L, where L is the length of the conductor. So as you consider these three rods, they have equal length. So when we consider that K into area of this is A into temperature is 5 minus T by L is equal to, observe that here we have 2Ka into T minus 3 by L plus 3Ka into T minus 2 by L. Observe that Ka gets cancelled on both sides. Ka by L gets cancelled on both sides. So remaining term is 5 minus T equals to 2 into T minus 3 plus 3 into T minus 2. So here 5 minus T equals to 2T minus 6 plus 3T minus 6. So here 5 minus T equals to 2T plus 3T is 5T, 6 minus 6, minus 6 minus 6 is minus 2. So here when we bring this T towards this side and send this towards left side, observe that 5T plus T is equal to 12 plus 5, 60 is equal to 17, then T is equal to 17 by 6. So at the junction the temperature is 17 by 6. Take a screenshot, we'll continue. Okay, let us consider three different areas. So area of each part is A, whereas the thermal conductivity of this part is K1 and length of this part is L, and here the length is also same as well as length is also same. So now it has been divided into two parts, K2 and K3, as well as it is a K4. So now here observe that this combination is having equal area as well as equal length. Now based on that we have to represent the resultant thermal conductivity in this case. Whereas as you consider that these two parts is having a equal length and equal area. So now based on that we can represent it as K dash equals, it's a parallel combination. Answer that K2 into A by 2 plus K3 into A by 2 by A by 2 plus A by 2. So now as you observe that K dash equals to A by 2 into K2 plus K3 by A. So A and A gets cancelled. So here we get A dash equals to K2 plus K3 by 2 is the resultant thermal conductivity in the case of parallel combination. When we consider series combination, observe that length of these three parts is same, whereas area is also same. And here already had represented the equation for series combination, whereas K is equal to K1, K2, K3 by, or observe that we had represented the equation based on series combination, and we know that R equals to R1 plus R2 plus R3, and here we know that R equals to L by Ka. So now L by Ka is equal to L1 by K1 into A plus L2 by K2 into A plus L3 by K3 into A. So now after that A gets cancelled on both sides, and here we know that L is nothing but same L. So when we substitute this, L by Ka is equal to, we can take L as common, 1 by K1 plus 1 by K2 plus 1 by K3. So here A gets cancelled and L gets cancelled. So here we get K1 by K equals to, we know that K2 is nothing but combination of these two thermal conductivities, nothing but K dash. So here we can represent it as 1 by K1 plus 1 by K dash, and here K3 is nothing but, third one is K4, 1 by K4. When we do LCM, here we get a 1 by K equals to K1, nothing but K dash into K4 plus K1 into K4 plus K1 into K dash by LCM of this is K1 into K dash into K4. Then K equals to K1 K dash K4 by K1 K4 into K dash plus K1 into K4 plus K1 into K dash, where K dash equals to K2 plus K3 by 2. When we substitute this, the resultant thermal conductivity of this combination can be represented. Take a screenshot. I hope that you have liked my video. Please give a like to this video, share this video to your friends, and don't forget to subscribe my channel.